Welcome back. This is the POE calculating forces for 2.1.6. You will need to be taking notes on this. This will be quite intensive. This is probably one of the hardest uh, units that we'll be doing and very heavily mathematical. So, first off, we got to talk about what's happening to a truss. A truss is the beams that support bridges are on the sides, or they're the roof, the members inside your roof that causes your roof to have that peak look. Those are trusses. And so we're going to talk about the difference between compression, so that's when it's squeezed together, and tension, being pulled apart. So here's an example of a railroad track truss. These are the trusses. We're going to analyze to see how much force is each and every single beam here actually have. So when the trusses are composed of these members, they're joined by either welded or gusset plates. This is a gusset plate here. And there you can also nail them in place when it comes to, if it's wood, but we're going to think about it as metal. A simple truss is just going to be simply a box. But if we push it, it's going to bend and then eventually collapse. But if we add one more member, it's going to become rigid. Now we're going to talk about pinned and roller supports. Pinned are when they are physically bolted to the side of a cliff or the other side of your river. They're bolted in both the X and the Y, so they're stuck. They cannot move. The roller is an actual like rolling pin. So you can see this is a cross-sectional area of the pin. And the bridge is able to roll left and right. So it's free to move left and right, but still prevents it from moving up and down. So what we're going to do is solving some trusses. But before we can do that, we have to make some assumptions. All members are perfectly straight. So all beams are perfectly straight. All loads are applied on the joints. All joints are pinned and frictionless. And the bridge itself has no weight. Now, obviously, these are not true, but it makes our life a lot easier, and you don't have to start adding in friction or any calculus into this. So, what risks might these assumptions pose if we were designing an actual bridge? All right, first we have to know, is this bridge statically determinate, or can you actually determine this mathematically by using the way we're doing it and not having to use a computer to do it? And if this side does not equal this side, you have to use a computer, which will then use software to solve for it. On the other hand, if this side equals this side, then you can use the method that we're about to go over. So it's 2 times the number of joints equals the members plus the reaction forces. Now we'll talk about what those all mean. So here is one. We got 2 reactionary forces, but each pin, triangle, is 2 reaction forces. One in the X, that keeps it from moving left to right, and one up and down. So you got 2 here and 2 here. So that's 4 reaction forces. Then we look at the members. 1, 2, 3, 4, 5. But then you have a number of joints. 1, 2, 3, 4. So this truss is considered statically indeterminate because the number of joints is 2 times 4, that's 8. But by having 1, 2, 3, 4, and then 5 members, that's 9. 8 does not equal 9, so that does not work. But as soon as you put a roller here, this now truss is statically determinate. 1, 2, 3, 4, 5 members. Now it's 3 reaction forces. This triangle represents a pin, so it has an X and a Y. And this only has an X because it's allowed to move in the X direction, but it keeps it from moving in the Y direction. So that's now 3. So now we have 5 members plus 3, that's equal to 8. And then there is 1, 2, 3, 4 joints times 2. It is now statically determinate. So I want you to look at this. You can see how there you have all these joints here. And if we look, there's 19 dots. If you counted all of these members, you would actually get 35 members, and there's 3 reaction forces. This side is penned. It is bolted into the earth itself, but if you are careful and if your screen is good enough, you'll actually see that there should be a little roller right here in the shadows that allows the truss to move in the left-right direction. So this is statically determined, and you could calculate all the forces on that truss. Now here's the equations that we're going to use. Sum. Remember, this symbol means sum, meaning add up all of the moments have to equal 0. So this is not going to allow any rotation. Sum in the x directions has to equal 0 because it's not moving in the left-right direction. And the up-down direction, the y direction, they also doesn't, because your bridge is not moving up and down. If it's moving down, that means it's falling over and, going into the river. That would be bad. So now using moments to find your reactionary force at point C in the y direction. So what you're going to do is pick one of the points, either A or C is what I would recommend, and imagine if you put a big old thumb there, and if it rotates, what would it rotate as? So what we can do is we can say it's going to rotate either clockwise or counterclockwise, and you're going to then do the math. So we're pretending that we'll put a big old thumb here, and we're going to rotate it. So this rotation at force, the reactionary force at point C in the y direction, is going to move it up by this distance plus point D here pulling down times this distance. Now that's going to counteract each other, and so the 500 pounds times 3, which gives us that number, has to equal the reactionary force times this distance. And that, you do your algebra, and it comes out as a total of 150 pounds. So the reactionary force, the earth itself, is holding up 150 pounds in the upward direction. Then we do the same thing, but we're going to solve for what we call ray, or the reactionary force in point A in the y direction, which is pushing up here. So we sum all of this. So this y going down has to equal this plus this going in the up direction. So, and now you notice that's the negative, so it's going down. So it's negative 500. So plus ray, we already solved for this one. So then we solve for ray, and it's 350 pounds. Rax is convenient because there's only one going in the left-right direction. There's no other forces. So that means that Rax is equal to 0. And then we'll continue on the second video.